Ladies and gentlemen, a very good evening. My name is Lam Chong-ik from Agilent Technologies. Today I would like to share on some recent improvement on Y-factor noise figure measurement uncertainty. In the next 15 minutes, I will go through following agenda, starting with noise figure overview and Agilent noise figure measurement solutions. I will spend more time on the last sections, which is talking about some recent improvement on the Y-factor noise figure measurement accuracies. A key takeaway will be the introductions of the USB preamplifier, which helps you to have to make more accurate noise figure measurements and also improve Daniel performance. Let's start with some refreshments on noise figure basics. Why do we care about noise? Noise degrades our signal qualities, hence causing higher errors in your communication systems. This is not desirable. How do we improve on that? We can increase our transmitter power to improve the signal to noise ratio, but this might not be practical. Why? Because there are a lot of limitations on this. We have to take care of regulations and cost. A more practical solution is to lower the receiver contributed noise by using an LNA. In order to be able to address the noise issue, we need to be able to quantify the effect of noise. One of the ways for us to quantify the effect of noise is noise figure and noise factor. Noise factor is defined as the degradations of signal to noise ratios. It's the signal to noise ratio at the input divided by the signal to noise ratio at the output. It's a parameter where the performance of an amplifier can be specified. Noise figure is the noise factor in log form and is expressed in decibels. Next, I will share some of Agilent noise figure measurement solutions. Agilent has been producing noise figure measurement solutions for more than 50 years. The most recent instruments that can be used for noise figure measurements including the X-series analyzers and the PNA-X. In general, there are two ways to do noise figure measurements. First one, the Y-factor method, is the most common way of doing noise figure measurements. It's used by NFA and spectrum analyzer. For this type of measurements, you need to have a noise source with known ENR values to do the measurements. The second method, which is the cold source, is a newer method which is used by network analyzers. Y factor is a ratio of two noise power levels, one measured with the noise source on and the other one with the noise source off. And with this, we were able to derive what is the noise added by the amplifier. This is the most common way of doing noise figure measurements because it's convenient. You only need a signal analyzer and a noise source to do the measurements. Y-factor measurements using a signal analyzer is great if you are measuring connectorized device. We have a series of spectrum analyzers which can be used to do noise figure measurements ranging from CXA, EXA to the higher end MXA and PXA. What is needed is for you to get the options, noise figure measurement options 9069A. Vector network analyzer uses a cold source measurement method. For cold source measurement, we do not need to measure the ratio of two noise power levels. We only need to measure the noise power level when nothing is connected to the duct. Because the VNA is able to measure the gain accurately, we are able to derive what is the noise added by the amplifier from here. We can perform accurate cold source noise figure measurement using Agilent PNA-X with option 029. With this, we are able to achieve highest measurement accuracies of all solutions in the market. In summary, we have two types of measurement method for noise figure measurements. The first one, cold source method, which is used by NA, and the second one, Y-factor method, which is used by SA. Which one should we use? Well, the NA-based solutions give you very high measurement accuracies for noise figure measurements, whereas for SA-based noise figure measurements, we still able to get equally low uncertainty levels if you are measuring connectorized and well-matched data. And the SA-based solutions is less expensive compared to the NA-based solutions. Finally, I would like to share some of our recent improvements on Y-factor noise figure measurement accuracies. When we talk about measurement accuracies, the first thing that we look into is the uncertainty calculations. Our noise figure measurement uncertainty calculator was developed many years ago, and during that time, we did not have very good guidelines to do the uncertainty calculations. As a result, we overestimate our uncertainties by using 3 sigma and worst case value and assumed it as 2 sigma values. At the same time, we did not properly model our uncertainty, our distributions, and assume that everything is flat. Our measurement expert revisited the uncertainty calculators and redo it following GAN methods using the correct distributions. As a result, we were able to get better estimations with lower measurement uncertainties. We then relook into our noise figure measurement chain and try to investigate on the uncertainty contributors, which is shown over here. From our investigations, we found that a large fraction of our uncertainties comes from the noise source which we use during noise figure measurements. From what is shown right here, around 80% of the uncertainty comes from the ENR uncertainty from the noise source. From here, we know that if we're able to reduce the ENR uncertainty of the noise source, we're able to reduce our overall noise figure measurement uncertainties. So what did we do? Within Agilent, we did some improvement on some our noise source calibrations. At the same time, we have some improvement of noise source calibration between 18 to 26.5 GHz at National Measurement Institute level for our case, which is the NPL, National Physical Laboratory of UK. As a result of these two improvements, we're able to reduce our measured uncertainty by around 40% as shown at the graph over here. This has been reflected if you are sending your noise source to Agilent for calibration starting end of 2013. In summary, with the updates of our noise figure uncertainty calculator and with the improvement of ENR, our noise source calibrations, we're able to improve our noise figure measurement uncertainty significantly. For the example shown over here, we are getting around 45% of improvements. We then look into the graph of our measurement uncertainties versus the DUT noise figure and the DUT gain. Although we have done some improvement on our noise figure measurement accuracies previously, yet there is still some room of improvements, which is at these areas. We can see that the uncertainty is still high if you are measuring DUT where the noise figure is low and the DUT gain is low. So what should we do about this? From the uncertainty calculations, we understand that if we're able to reduce the system noise figure, we're able to reduce the uncertainty significantly. In order to reduce the system noise figure, we can use a preamplifier. With this, we introduce the U7227X USB preamplifier. This amplifier has cal data stored into the EEPROM, and when it's connected, it uploads the cal data including gain, noise figure, and match value into the X-series analyzers. It's all automated with the USB, that's why it's faster. A nice feature is that it corrects the noise figure and the gain when the temperature surrounding it changes. With this, it's more accurate. And then another nice feature is that the gain tends to increase with frequencies, which we optimize to compensate the noise figure of the instruments, which also increase with frequencies. We have a series of preamplifier ranging from 10 MHz up to 50 GHz. The USB preamplifier can be used as remote front end for normal spectrum analysis. When you connect through USB, you can get corrected display magnitude values. With the lower noise figure compared to the internal, the signal analyzer's internal preamp, we able to improve on the analyzer sensitivity, hence giving you lower Daniell level. At the same time, the USB preamp can be used to improve our noise figure measurement accuracies. When it is connected, it uploads the gain and noise figure data through the USB to the X series analyzers. With this, it's able to support internal cal. Internal cal is a nice feature where you can do noise figure measurements without needing to needing to do calibrations with a noise source. The USB preamplifier is best when you are measuring that with low noise figure, low gain, and high frequencies. This graph compares the performance of noise figure measurements when we are measuring with and without the USB preamp. The blue line over here is showing the uncertainty when you are measuring without the preamp. And the red line over here is showing your uncertainty when you are measuring with the preamp. The noise figure measurement uncertainty is always lower when you are measuring with the preamp. From the graph, we are able to know that the uncertainty improvement is significant when you are measuring that with lower gain and higher frequencies. We are able to get around 40% uncertainty improvements when we are measuring in a 5 dB gain, 5 dB noise figure that below 10 GHz. The improvement is more significant when the frequency goes higher. When we measured that with even lower noise figures, say 3 dB, we are able to get even more uncertainty reductions. For the case as shown over here, we are getting around 65% uncertainty reductions when we are measuring 5 dB gain, 3 dB noise figure that. The uncertainty reduction is a lot more when the frequencies goes higher. Let me re-summarize on what I have shared on the USB preamp. The USB preamplifier has lower noise figure compared to the signal analyzer's internal preamp. With this, it's able to improve the signal analyzer's sensitivity and have better Daniell performance. With the lower noise system noise figure, we're able to improve on our noise figure measurement accuracies. The preamp is designed to have positive gain slope, which is optimized to match with the noise figure performance of the instruments. This helps us to get better measurement accuracies at higher frequencies. That's all I have. Any questions?